Statistical Process Control, SPC, is used to control a critical process output acting on the factors affecting it only when required. The purpose is to differentiate between a statistically significant change in the process and common cause variation because the actions required will be different. You can see this presentation in Polyedrica blogspot. We will now analyze different SPC charts for variables and attributes. There are two streams to avoid. Overreaction, adjusting after every output, makes the process worse. Dispersion is increased. Underreaction is just as bad. A slow process degradation passes undetected until it is too late. SPC uses some rules developed by the Western Electric Company to detect symptoms of statistically significant variation. The center line is the average of all values, and the standard deviation is also estimated from all the values. In our Excel file, red dots indicate upward trend symptoms and green dots downward. These are the upward symptoms definitions. Download this Excel file from OneDrive with the examples we will use. In sheet change, we have collected process yield data every hour during several shifts. Since we collect a single value each hour, we are using a variables SPC chart for individuals. This chart can be complemented with a moving range chart where the absolute value of differences between each value and the one preceding is plotted. We automatically apply the Western Electric rules for out-of-control symptoms, and the alert description will appear in the corresponding row. When any of these alerts appear, the corresponding point in the chart will be colored in red if it is upward, and in green if it is downward. While there are no color dots, the process is stable. There are no statistically significant changes. Let us now analyze the results of this chart. We see green dots from 10 hours to 16 hours on the 10th, and red dots between 1 hour and 3 hours on the 11th during the night. We can notice a jump from 16 hours to 17 hours, which might indicate the moment when the process has changed, but this jump is not significant enough to declare it as a process change. It is not until 1 o'clock that we have enough evidence to declare that the process has changed. In this case, since we are measuring yield, an increase in yield is an improvement. So we can say that the process yield has improved sometime between 16 hours and 1 hour. With this information, we should now investigate what happened during this period of time that caused this improvement. How much have we improved? If we compute the average between 6 hours and 16 hours, we get an average yield of 93. And from 17 to 11, the next day, 118. So we can estimate an average yield increase of 25. Looking at these alert details in the bottom rows, we see that from 10 hours to 16 hours, we have 4 out of 5 consecutive values 1 sigma below the center line. This is an indication of values significantly below the average. The value -9 at 14 hours means that the last 9 values were below the center line. That's also a significant trend. The SPC chart for individuals we have just used has a condition for the validity of the results. The data should follow a normal distribution. So we will now check for the normality of this data with the sheet Basic Stats. We see the histogram, which doesn't seem to have a bell shape, but the p-value of 0.351 for the test of normality is well above the alpha of 0.05, so this confirms that there is no evidence of lack of normality. The X bar and S is a common SPC chart for variables. Instead of making one single measurement, we make several, in this case 4. In this example, we have taken 4 measurements of a critical dimension every hour. Each hour, we compute the average and the standard deviation of these 4 measurements. We use 2 charts. In one, we plot the averages, and in the other, the standard deviation. We apply the same Western electric rules to each of the charts. Any out-of-control symptoms in one of the charts will indicate a significant process change. In this case of a dimension, green and red dots in the average chart are equally bad, significant deviation from the average. In the case of a standard deviation, the interpretation is different. Red is bad, variation increase, and green is good, variation decrease. Operators must be trained to interpret these out-of-control situations in order to make the required corrections in the process as soon as possible. Here we can see the specific symptoms alerting each out-of-control situation. The different symptoms may require different actions from the operator. Looking at the chart, we can graphically detect an upward trend, which in this case of yield is a good thing. Our process is improving significantly from the statistical point of view. This trend is confirmed by the green dots followed by red dots at the end. Here we are collecting daily production data, and we notice that our average production is 400, and our individual SPC chart is not detecting any significant changes in the process. On the other hand, we can see a repetitive cycle of 7 days, which of course corresponds to a week. If we look at in our calendar the days of lowest production, we realize they correspond to Sundays and the next lowest to Saturdays. This is telling us that maybe there is a significant seasonal trend within each week. We have added column C with the day of the week calculated with a formula from the date. We then computed the confidence intervals for the average production of each day of the week. From this Gantt chart of the confidence intervals, we see that Wednesdays and Fridays have the highest production, and all the other days, the average production is significantly lower. We have been collecting daily process time during 3 months in sheet time, and we want to know if there are any significant changes in the process during these 3 months. Since we have a single value each day, we will use a variables SPC chart for individuals. We need our values to follow a normal distribution in order to use this chart. So we will do a test for normality in basic stats time. We can clearly see a very skewed distribution, which is far from normal. This is also confirmed by the p-value of 0 in the normality test. This is what we would expect. Time measurement typically follows a skewed distribution for a simple reason. There is always a physical lower limit in time. On the other hand, there is no upper limit. Time may be extended by all sorts of defects or difficulties. This means we can't use an individual chart. In this case, we can look for a data transformation that will make the data follow a normal distribution. This is a data transformation of the sort y equal to x to the power of lambda, where we calculate the value of lambda to produce a normal distribution. We will calculate this value from the time data in column A of sheet box Cox. To calculate lambda, we will use Excel solver. We calculate lambda in cell I8 by maximizing cell I6. The restrictions are that lambda should be between -5 and +5. The resulting value is lambda equal to minus 0.348. In column F, we obtain the transformed data. We will check now if this transformed data follows indeed a normal distribution in sheet basic stats transformed. Checking the normality of this transformed data, we obtain a p-value of 0.717, which confirms that this data is now normal. P is greater than 0.05. Now, we can use an individual variable's SPC chart with this transformed data in sheet SPC transf. So we are controlling with SPC the transformed data instead of the original data. And we see no out of control symptoms in this case. Our process time is stable in spite of its high variance. This means it has not changed significantly along these 3 months. In this case, we want to control the daily proportion of defective units, so we need to collect pairs of values each day. Sample size, which is the number of units controlled during the day, and the number of defective units found. The proportion of defectives is P equal to defectives divided by sample size. It's what we will control in the SPC chart. We can't use collect the proportion P because we need the sample size for the SPC calculations. If you look at the upper control limit in red, you notice that it is not a straight line in this case. The reason is that the sample sizes are varying, and this affects the control limit. The larger the sample size, the lower the limit. The average proportion of defectives shown by the center line in blue, which in this case is 0.01, that's 1% defectives. The Western Electric rules still hold in this case. We must distinguish between defectives and defects. A unit is either defective or it isn't. So the distribution of defectives is binomial, only 2 possible values. On the other hand, one unit may have more than one defect. So the distribution of defects follows a Poisson distribution. The aspect of a Poisson distribution may look like a variables distribution, but it is very different. The Poisson distribution only has integer numbers in the x-axis. An individual unit may have 2 defects or 3, but it couldn't have 2.8 defects. DPU can be any real number greater or equal than 0. Sheet U has an example of a U chart. Here we have used a pivot graph to plot the distribution of defects in the samples of 10. These are some conclusions. SPC is a useful tool for operators in order to control their process by making the required adjustments as soon as needed, but without overreacting. Control charts are useless unless analysis and corrective actions are done in real time. To do this, data must be collected on the spot and charts updated fast enough. Operators need to be trained to know what corrective action is required on each case. Variables SPC charts of critical process parameters are more accurate than attributes, and they enable process adjustments before defects start to appear. variables charts for individuals require normality, so you may need data transformation. Being in control is not enough. We must make sure the process meets the customer requirements. Process capability measures to what extent is a stable process able to meet these requirements.